Now we go mode. Again, if you have problem with the session here, make sure that you use your audio to interrupt me because I won't be able to see your text. Okay, so last one is also we have a new called tangible user interface. I think you're familiar with this, but I'll retouch on this one. Okay, and then the second part of this lecture is going to be on spatial augmented reality, which is different than what you had done before in using the camera from the first person point of view with either headset or the mobile phone. All right, so the concept of tangible user interface is pioneered by Professor Ishii. Okay, I upload this to a reading, so you can go and take a look into that. Okay? So he gives some basic design of what tangible user interface look like. Okay, in that article would be a good idea. So he leading up at the moment at the Media Lab MIT, so on doing some things like this. Okay. We see some very interesting and cool example later on. So the idea here, this is from his one of his lectures, one of his image. He basically tried to conceptualize what is the key characteristics of a tangible user interface. What is it? Okay. So what he came up with was three components. Okay. So layer. First is called tangible representations, physical object itself. So in this case, you can see in the diagrams, tangible representation there. Okay, so dark purple. Okay, and the second layer called physical control. That would be the interaction part. Okay, so in that case would be a little light blue just below person hands here. So that's just illustrate or symbolize the interaction part. Okay. But then you have the third one, so which is the intangible representation, which is a sub or divide between this physical and visual divide. Okay, as you can see here. Okay. So in that case here, you can get a sense of what information might be. So this is how Professor Ishii was trying to see, okay, the interaction before it used to be only the physical component or only digital component part of it. And the physical is really just the keyboard and mouse and things like that. But in this case, the object that you're interacting becomes tangible itself. Okay, so that was a new concept 15 years ago. There are many names leading up to that, but I think TUI, tangible user interface, seems to be the one that most commonly used that technology. So the idea here is really about the impact interface to affordance. Okay, so this is a new concept here. Okay, so affordance is the ability to recognize from the looking at the object itself whether what is this a mouse, is this what is it if you haven't seen them before. So affordance has a bit of a cognitive attribute to it. Okay, so people can recognize whether they can recognize that they misunderstood. So in this case, it's a very simple, basic idea. So you have physical interaction to go from left to right, the input to the physical digital scene, the virtual scene on the right-hand side. So you interact based on the keyboards and things like that, or mouse design that you would have currently. Okay, and you have a feedback, which is that what's shown on your screen. Okay, they come the other way around from the virtual to reality back to you, and you make adjustments accordingly. Okay, so this is a basic paradigm that we've been governing the way we interact with computer for many years. It's still for most of it, laptop, computer, lab, only when it starts to move into this space, when actually the tangible, the interaction and the feedback become all one in one scope. And that's what we call the tangible user interface there. Okay? So the next example will show you some work here. Okay, so this one is actually the music has the music, and then they're tweaking the tone of the music. But still, you won't be able to collaborate to hear the audio, so you have to go to that YouTube link and see it. Okay. So but this just gives you a basic. You can see they have the visual representation as well. So this is a table. So this is a table as well. Okay, so people can use interactive table, so you can move them around like touch screen. Okay, and then but the object itself is a box, a little cube that they put on it, and then the table recognizes. So this is what the interactive table to look like. So essentially, the table has a projection of the camera on the bottom of the light coming up, and that's why you don't see the shadow of person hand. Okay, because the light comes from the bottom. Okay. Now the light, not only that, they also have a intermediate infrared light you cannot see. It's specifically to highlight the pattern just below that object. There's some 3D marker there. Okay. So in this case, it's what on the surface of those cubes is actually what is being recognized. But it's like only the one at the bottom, because that's where the sensor is below the table. Okay. And then how you rotate them, where they are related to their interactable components is important. So you can get a sense of the tangible that become together. So in this case here, different cube do different things. So like that one, the one they just put on the left-hand side, so they provide a sinusoidal to the signal, to the music that they play. Again, this music is being turned, the pitch and the sound are being, the volume are being moved around based on their interacting with the physical. So that becomes the intangible component representation in the diagram previously, which allow you to see the changing platform in front of you. Okay. So this is they're just showing off different components that they have to program. They'll be available in their application. That they link together, they can link systematic. You might have seen that this is looks similar to a graphical programming, which is indeed the concept the same, except that you're not actually using a keyboard, using the mouse to drag and drop from a drop point. So you essentially use the object that has specific properties programmed into. And again, they're programmed to the symbol that you have underneath that each of the objects. And you can see all the visual representation of that. That is basically pre-compute based on rules. Okay, you would have seen in an early few, I think a month or more ago, about this kind of interaction with different objects. Vuforia in some way is based on something like this, okay? But not this kind of technology, but it's sort of in terms of interface metaphor, it's a similar concept. Okay? So it's different concept, because when I think Ron tried to point you out that he was, the Vuforia was, okay, let me finish it. The Vuforia actually is supposed to be printed out in the paper, or this image target, printed on the paper, and you put on a piece of object. For example, like this, you could put a target here, and then you can move the target around with respect to the camera or camera altogether. Okay, but for the convenience of the way that we develop, the way we deploy and show it in the tutorial, so using the screen as that. Okay, but try not make sure that you don't limit yourself to thinking that because Vuforia was actually supposed to be one of those. And then I think in the next couple of weeks, Ron will show you, or you can go yourself to Vuforia that has a different type of target. So some of them is a cube. Okay, so that means you have 6 size image come out, and then you kind of print it on the paper, cut them up, and then build it as a cube. So the cube will work like the cube that you have seen in Retractable project here. So the tangible representation here is a cube, or this object that you see. Let me see, like, yeah. So all these cubes are a representation. Okay. So what's a physical control? So that's you can see here people are moving their hands around objects. They move around different objects, rotating. That's the important part. Okay. Basically, you rotate, you're adjusting the volume, different things depending on the property. And what is an intangible one? It's a sound pitch that happens. Okay, it's intangible. It's not, and also one thing that I should add is also the projective control. Okay? So that's projective content. Okay, so that is what output will look like. So the sound, and you have the content that projected, all the symbol that happen, the line, the link between the two objects, okay, that linking in some way, metaphorically linking between the physical content and the virtual content. Hopefully, that gives you some a bit idea. This one I can play quickly, but this one we look at this before. Okay. So this one is IO brush. Okay, so this is the same thing. But try to think about in terms of concept here. You have a hand controller. Okay. Mm-hmm. So this one was like it before. So just not going to have to play with the whole thing. Okay. So in this case here, the tangible representations are really the brush itself. You can see here people now the concept of affordance allow you to be able to see it, what's supposed to do with it, rather than try to click this button and see what it's supposed to do. In this case, we build based on the mental models that most people would have. That's where how you design to the target audience. Okay? And then what the physical control. So in this case, it's a natural handler. Okay, so I think you can get a sense of what there might be, because this is it make it easy, but you need to think about how people to engage with the content. Let's say the contents here are not designed aside from Blush, the Blush thing. Blush is really the mechanic in which they designed this one too. Okay, so think about what happened is just want to people to engage with the everyday contents or texture around them and put them together in art, in some sort of art, media, or editable digital form. Okay, so the Blush becomes something that they develop as part of the interface they come in to allow that to happen. Okay. So intangible is basically the color and the textures. They come with whatever they scan through this Blush, which has a camera hidden inside. Okay. And then output here, similar thing. So they have a projective painting on the screen to allow people to imagine what their content. Okay. You can think about these can class as an altering tool as well. So you kind of try to altering an art form and then rely on this object, on this physical content. So I think this one I show you before, so you can see the sense of what inside that. There's a camera hidden underneath, and then there's LED illuminating the light, the touch sensor there to detect whether it's actually touched or not touching. So that's a kind of simple concept. But try to think about this. This is not just you want to build a block. Okay, so this one is more or less you try to do a tool that address these issues, generating and ordering people to use it. Okay. This one is a very interesting one. Okay. By MIT. Okay, so this one is the physical. It comes in the tangible. You can touch on it, but you get a sense of what remote check hand or remote handling of virtual remote people look like. Okay, so let me take a video. Again, come from Media Lab. This is all read by Professor Ishii. So this concept is very good. Okay, very interesting to look at. Okay. The red ball is the physical one. Okay. So the remote person will come through the video that you see there. But that hand projection of him in front of that is a little cube, the micro actuator that pushes from the bottom. So generate those. From your end, you will feel a sense of that extension, remote extension on yourself, but this is from his end. So he can see the live view of that red ball from the other side. Okay. And you can put it in here like this. You can see the object there. It's a very interesting concept. Okay. It basically extends his presence into the real. Okay, now they're talking about collaborative a little bit. Okay. So these are just showing off the background of what the device can do. Each one of that unit pin is a micro actuator that push from the bottom up, and they have a projector at the top. To emulate the light, provide intangible representation like projected content. Like this one, they can demonstrate the graph with different colors based on their height. I think that was a really quite interesting one. So this one, it has, as I said before, there's a projector and there's a camera to recognize where his hands is. So that's a 3D plot. That's a graph representing the equation. So this is the actual system. Let me see if I can pause here. You can see here the actuator at the bottom. Okay, actuator there, computer run. All this is actually actuator pushing up all this. And you have projector projecting, giving a light, different light to that neutral color bar. And you have a Kinect. Kinect is the depth sensor. If you haven't played the game before, Kinect is the depth sensor. You can detect the foreground and background. You can detect the gestures and things like that. So it allows you to interact in that way. So it's relatively complex system, okay, but it's really neatly put together. So hopefully, you can go and watch the video again if you want. So it's kind of extend the idea. Okay. Let me. So that is a tangible user interface. Okay, as I said before, that one is closer to Euphoria as far as your tutorial and your assignments for is concerned. So you can think about that, putting object, a marker in a physical object, things like that. Okay. Now the next one here is called spatial AR, okay, augmented reality. I'm having trouble uploading the books, but I'll upload that after the lecture, along with a copy of slides. But this one is quite complex issues. Okay, spatial AR here, okay, is really in general it's a spatial display that detach the display technology. Okay? You're no longer wearing or holding a mobile phone or wearing the headset. So now it's basically used to be called a projector-based AR. So essentially here, the user experience this part doesn't have to have any equipment with them. They just go through like a classic example with a museum type of setup. So that one is project-based AR. So you have real-world objects, you have projector, you project into it, and then you have the user. Okay. Sometimes the user has a bit attached to that viewpoint as well, is potentially head tracking position in case that you need to generate what we call a stereoscopic display. Okay. Because remember, projector needs to know where you're looking. Okay. Without the head tracking, they wouldn't know. So that's still possible if you just like the example before the micro actuator. If you just simply want to put the same color, there's no sense of depth. In that case, doesn't need to because the depth is actually generated by the 3D structure of the micro actuator anyway. But in this case, the objects are not moving; it's a fixed object. So in this case here, the advantage to this one is offer much higher visual resolution-wise, field of view than HMD. So for those who come to practicals, you will have seen the HoloLens has a very tiny window of 40 by 30 degrees field of view, so very kind of tiny in front. So, but the projector display, as you can see in a normal classroom or in tutorial, the kind of projector is very big. Okay. The advantage here is also you don't need to calibrate it every time you want to use it. Okay, like in AI headset, oftentimes you do need to adjust the space, everything, make sure all tracking system around the headsets are working and everything, so find the ground, things like that. But for these one, it's more, it's one you lock in, Well, in some ways, a good thing is that you don't actually have to do it again. Okay? However, that becomes a disadvantage as well, because it's really not when you lock it in, like setup, exhibition setup, it becomes very difficult. You don't want to recalibrate it unless you have to. Generally, the recalibration nowadays probably should be relatively quick, but it still takes 10 minutes or so. Generally, calibrations are required. You project a pattern light, okay, the light that has a pattern like a chessboard or stripes and things like that. You know trajectory beforehand into a space, okay, that now seemingly different than previous completely calibration. Okay, so when you do a calibration, you scan the space with pattern light, and you have the camera to look for those patterns. Okay, look for those patterns that change, how patterns change when they reflect off the physical space. So that becomes sort of around the advantages and disadvantages around that part. It's easy to set up, but once you set it up, then people can just walk in without required to adjusting any of the headset. Okay. So the basic concept of these is really playing around with the projector here. This is just to show the foundation. Mathematics, you can look inside that book. Okay, that book has 600 pages. There's a lot of mathematics in there. So you can go and look at that if you have special interest. In this case here, if you have normal projector in the classroom in the tutorial, they tend to do like what the left-hand side. You project 90-degree angle, so you get a perfect good size square rectangle shape of projection on the screen. Okay, this is only top view, but then projector here could be coming from angles. Okay, so coming from angle, just like image on the right hand side here, coming from slightly from the angle. So what would that mean? It's actually shape in which it reflects onto the into the screen, the 2D screen. Try to imagine that this fundamental concept is changing into because whatever is not a 2D screen, it becomes a 3D object, a physical object in space. And the camera are not just changing in one direction. It could be a 3-degree of freedom, change different types of angles. So that means is that a lot of projection, you need to think about how to distort it, recalibrate the image that you project so that it appears properly on that particular physical object. Okay, so that is the fundamental difficulty of these techniques, because you try to use the physical space to play with this. So there's one concept there. So the multiple projector. Okay, so this is over planar surface, meaning flat. Okay, so calibration techniques. That one is a known project known pattern. I said earlier, like chessboard or pattern stripe, black and white to row after row, and then you completely overlapping between different projectors. Okay, that's the difficulty is. So let's say one projector can only go, even though it has high field of view projection, it's only cover the object in one point. The back end has to be come from a different projector, and if the object is big enough, you probably need the one in the middle, transmit between the front and the back. You have something on the side. Okay, so this is one. Then I think I might have alluded before, and then now you have projection here. You know the pattern you're projecting this, and then how would you correct for that? The first step for that is that you put the camera there to capture what they are, what is the distortion are, what the difference are of the projection pattern. Okay. So this is work from UNC, University of North Carolina. Just show the basic case here. So you have a wall, the image on the left here. Okay. You have the wall that has a kind of edge on the tool. Okay, so I'm not sure you can see my mouse here, but see here the red coming and intersecting, overlapping the blue on the right hand side, and the green coming from the bottom. Okay, they all have different, just like a pie chart, overlapping pie chart. Okay, the idea of these is creating a virtual projection of a column that appear to be on the flat wall. Okay, so in that case, is that a calibration we need to take a pattern. So the image on the left, so you projection different colors there, and then you're also looking at the shape. Okay, shape look different here, but all the projection come with rectangle with the typical projector. So you can see here with the camera, just like what we said before, with the camera like that, you can capture this distortion and overlapping areas. Okay, that actually you can actually recalculate that, and that's what it's actually doing for the whole thing here. It's like recalculated, okay, what angle of that camera or of that projector related to the physical space. Okay. So once you have that, you correct for it, okay, and you're creating a correction factor for all these projectors to correct the image before they project it out into the space. And that's why all configuration here should not move or cannot be moved while doing the after the calibration. Okay. So once you have this, the image at the bottom right, okay, so that's changing into a one platform. So technically, you shouldn't see much of the seam of the wall of partitions. Okay, you just see them in flat. Okay. Of course, there was a lot of work has to go into that space. A lot of computation. So parameters can take hours to calculate, okay, especially if you have more camera and you have more projector. Okay, if the structure of the plane. So this one is really simple. It's a planar. So we know something, one certain fact that the wall you project to are flat. Okay, but there could be multiple walls. Okay. The next thing that could make this a little tricky is called non-planar. So this one is that you are actually projecting to a curved area, curved space, okay, unlike flat planar surface. Okay. So in this case, how will you do that? Now you can project a pattern light, you can project the light, okay, but how would you actually fix it? Because you no longer know the space in front of you, what it look like, what the curvature look like. You no longer have that. Okay, that's why the calibration is a little bit more complex. Okay, generally require that you have a physical calibration pattern. Okay, oftentimes like a chessboard or some object that you know what they look like, and basically put them into space. Okay, so for you to actually be able to capture the camera, and then you basically capture back and say, okay, that's how my fixed pattern that I projected out. Calibration pattern are distorted based on the pattern that I know. In the planar tracking is straightforward. Just you know it's flat, but this one you don't know. So that's why you introduce the alien object in there. In this case, a little square cube here. Okay. So that's all. That's kind of simple over the kind of very high level kind of explanation. Okay, so how will you do that? But in terms of mathematics, of course, that's quite complex. Okay, so and where you place them is also quite complex. So you can think about this as you're solving multiple equations, and you need to find a converged solution. Because sometimes if the placement of that physical calibration patterns are not at the right location and not sufficient to solve their multiple equation problem, then so basically you won't be able to convert and find the metric in the end. Okay, so that's a complex issue. We don't need to go there for this unit. But again, you can go to that book that I will upload it, and then you can take a look. All right, so this is another thing that people are looking also is overlapping intensity. Okay, so because now you have multiple projectors, there will be certain areas that are more brighter than the other. Okay, so because they have multiple projectors sitting on it. For example, this one has overlapping right in the middle of the image on the left. You can see that that's exposed by 3 projectors. Okay, projector here has a projection pattern on it. Okay, you can see here. Okay, so you can see that the middle is a little bit brighter. So that's one of the things that these people, researchers in this field, are try to compensate for that. Okay, so what they're using is called a concept of masking. Okay, so masking is really nothing more than you should try to manipulate the pixel intensity before you project it. So that's why the projected 3 here. So this is center area here is the most dense. There's more light. So you just basically adjusting in each of the projector the intensity in that overlapping area to be less. Let's say in this case, instead of intensity to be one full length, so you have 3 times intensity sitting in the middle. So in this case, you just divide it up. So you just intensity one basic concept. It's just divided 1/3, and then you have 1/3 from the other 2 projectors. Okay, so that try to help smooth out the luminance or the intensity of what is being projected onto the wall. So the mask will look like this. Okay, so the black one here is a more or less you don't continuate anything. So you can see the projector 2 here. Most of them are white, okay? And then you have the black when you have overlapping area. You have a little bit darker for intensity. So this will manipulate directly into the graphics, okay, before you project them out. Okay. Now, this is a normal relative experimental setup. You can see here there was a projector here, and a project on the left, in case you don't see my cursor. Project on the left-hand side, the right-hand side, and the top, okay, and the other projector. And the model is a Taj Mahal in the middle, okay, with the neutral color, the material. Okay. And then you have the camera. In this case, they're using depth sensor. Okay, so the camera on the tripod. You will see that. Okay, on the back left side. So that with that setup, okay, you go through the actual process. Okay, so you have this wooden model taking in neutral surface. Neutral surface here oftentimes make up a retroreflective material, okay, or something that doesn't reflect the light into the normal reflection. So the reflection in this case is that if the light goes through which direction and it's coming back in the same direction, like you throw a ball into the wall, it comes back to you. Okay. So in this case, if you throw the ball or throw the light in the angle into the wall, the light will go the outside. It will reflect off. Not just like you throw a ball with the angle to the wall, it just go away from you. Retroreflective materials is actually just doing that. The job is basically whatever angle you throw in the light or you shine the light to, come back the same direction. The reason they have to do that is that they're trying to avoid the problem of reflection, okay, which is going to be really hard to control them within the content, the object. So that means you get reflection everywhere. Okay. So in this case, if you get that material, so that's first thing you start with. It's a neutral physical model with a neutral surface. Okay. And then you start to illuminate by first projector. So this is doing a calibration. Okay. So you have 2 projectors, okay, and then you have 3 projectors. So you go one by one. So you have one first projector. In this case, only talk about 2 projectors, left and right, of the one on the top. And you can see here on this side, this is from the first projector, which is sit on the left to the model. So projected, you can see all this pattern, okay. So this is, we're talking about the image on the top right, okay. And you can see on that side, on the right-hand side of that structure, the package is the same. There's no color, there's nothing, no texture on them. So now we're moving on to the next stage, which is the area illuminated by second projector. So in this case, you can see here, second projector is to the right. So therefore, you can see it to the right. So you can see that actually the opposite happened. So the texture on the left-hand side are not there, not really seen, because that's part of not reflection. Now, if you illuminate them both on both sides, technically it should look like that, okay? But without calibrations, it won't look like that, okay? So that means you have to go through the process of putting a pattern light, calibrate using a camera, observing it, okay? So to make sure you're correct for distortion and everything, optical correction or this distortion to correct so that it doesn't look like the wall was tilted, because simply the angle of the projector are different than the angle of the object. So that's what you have at the bottom left. But you would ask, well, when you all do this all sophisticated component calculation, what exactly you can do with them, okay? So one of the things that they used to show off, hopefully the GIF image come off, is to create a virtual shadow. Okay. So in this case here, the projector are control multiple, the 2 projector are control as if you have the virtual light source moving around the top. Okay. So you can see here the texture being blended on both sides. Okay. Hopefully that effect goes through. So that was the idea. Idea is for people to come in, they don't wear any headset or mobile phone or anything. They just simply see what they look like. Okay, so this is just one effect, the virtual shadow. But you can actually think about application that go that like a museum type. Okay, You can see the skeleton of dinosaur, maybe missing component because it's very old. So the VR projection could project it onto them. Okay, so that would be something that very useful to look at. So that means that the material will need to change a bit there. So they need to provide texture, maybe the change in the projecting what the color look like over the year. I think that's and one other thing of these is that people are really projecting from the bottom. So in this case, the kids can look around, they can go to content, they can see up close, okay? And there's no attachment equipment required. Okay. Of course, it doesn't mean it easier. It means the pre-work a lot more. So some of these projects are showing off here. This one is a bit more complex, but it's a similar concept. Okay, it's projecting from the bottom. Okay. Let me try to get this. Okay, let's see. Let me scan it back. Okay, so this is a virtual showcase. This is they're putting a half side, half mirror. Okay, and then they take out the lid, and you can see the mirror in there. Okay, convex half silver. So they put kind of stand in there. Okay, just empty stand, rotating. Okay, they put the lid back on. And that's they put the object on the top. So that's it consists of the head tracking. So when I turn on the light, okay, inside, so you see the physical object in there that coexists there because it's a mirror, half mirror, so you see part of the light come out. Okay. Now, projection is still rendered from the bottom. Okay. And now the image of lions appear to be in the center. Okay. But really, what is happening there was this is a virtual lion, and it's project from the bottom to this illusion of going to the same screen. The half mirror that you see a case is at two ways. You get the light from inside out, and you've also got the light from from outside in. Okay, in this case, it's a reflection. It's similar to the case that you put the AR content in front, but in this case, AR content is really on the surface of that concave mirror. Okay, which appear to be there. Now, computation here a bit tricky. You can see the head tracking on the top because that is allowing you there to control the direction in which you're looking at, and also is a control the speed of the shutter glass. Okay, and generate you a 3D map, 3D perspective of this. If you remember, the projection you come out is just a single. However, the shutter glass is the left eye, right eye. Okay, it's generating the stereoscopic image for you. But you have to wear a shutter glass. So this is the kind of magic behind it. Okay, it's the image geometry of the object is project in the surface below, and then basically for them to be able to convert that to image the right proportion on the column there, you need to project distorted image that you pre-compute beforehand. That you say, okay, with the curve of that curvature, how much I need to correct my model so that my model is going to be created on the column that look proportionally correct. Okay, it's similar to the concept that we have before with the screen and the wall and projective wall. Okay, so it's really a combination of what your screen projection look like, what your objects will look like. So you can see here, this one, the image is moving around on the table. Okay, it just keeps changing the shape there. Okay, based on that. But generally, they are same table, same concave. The angle will be similar. Yeah. Yeah, there's always the trade-off of resolution. Yeah, so this one's, I think they will show the final product. So you can see here, this is the diagram behind it. Okay, so this is a planar mirror beam splitter. The idea of that one was a concave, kind of a half both sides. Okay, this one is a bit planar surface, but this kind of idea is the same. So you have projection from underneath the table. Okay, your eye view here represented by these eyes, that kind of two eyes on from different sizes. To look at the same object, you need to have image that originates from within, mixed with the one that you projected out. So that's the basic concept of AR, okay? Which is you're putting contents kind of mixed at the level on which people perceive the physical object. Okay, then appear to be augmented contents from that. Okay. The trick here is really mirror. It's just like a magic trick. So you need to have a mirror that's at the right angle so people appear to be at where they are, but in fact the image is projecting from somewhere else, in this case at the bottom projector. Now the concept here has a bit of, this one is a bit less of that calculation, but it's still done by Microsoft. Okay. So this is Luma Live. Okay, so this is built based on the work for their Magic Connect. Try to turn the room into a physical gameplay. Okay. So there's probably 7 projectors. Okay. And each projector triangular basis space. This is the calibration process. So they project a pattern there. And each projector of the 7 projectors, each of them has a companion camera on it. Oh, Connect, they use a Connect, so they have RGB camera built into them already. Yeah, so in that case, you can see the Connect and the projector. Projector is a big white one. The Connect is a little on the top there. You can see the top. So the depth the sensor has camera, has sensor depth, and then they have, and that is a constellation of the multiple projector setup to cover the room. So that's the pattern what I used before. This is a fast time lapse, fast forward. So they send in the tab, and then they have the camera. They capture what the distortion of the environment looks like, what little corners, sofa, and everything. So they recognize the structure, and they build that structure accordingly. Okay, so let's just finish all this pattern. And then that's what the point cloud that they generate from that scan of real world constructing. That's the structure for motion. So that's quite a different setup that they're doing. Okay, so in this case, and then they further on, they use algorithm to distinguish, oh, that's a vertical wall, this is a wall, this is a floor. They're already doing that. Google AR cores are like that. Okay, so they are very specifically designed to detect the plane, the cloud plane. Okay. So now you can see them in action. People walking around, shooting, step on the actual object, okay? The projected and monster. Okay. This concept have been used to extend, for example, let's say you have a TV, but you want to extend your TV beyond the physical size of your television. Okay. So in this case, you should protect the wall behind it, but you need to correct for this correction for all these different angles that it has, okay? And not at the same level plane as well. But other technology we've seen before, like a table, and they're actually hidden the projector beneath it. This one is out in the open from the ceiling, so you see from time to time the cast of shadow, okay, of his own shadow, the user shadow, that become a part of their limitation in terms of interacting. But they can project to the physical there. But you notice that they cannot accommodate on the fly the people who are not in their calibrations. So that's what I mean, all the players. You will see the projection right on their back. Okay? They're unable to accommodate for that. So this is to showcase what the spatial AR look like. Okay. So that's hopefully give you a sense. We won't have a chance to look at that in the practical session. Yes, so we don't have an application for that. Okay, so that would be the end of lecture today. Let me answer a few questions here. Mechanical. I'm trying to look at what Ethan's have here. So many mechanical parts to fail. Yeah. Are you referring to what exactly? Oh, okay. So you're talking about you can see your mouth. Mm, 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 mm. Mm. Yeah. So yeah. So there was a bit of that. So I'll take a recording to see whether it's any major problem with the recording. Otherwise, I have to re-record them. All right. So let me stop the recording. Any other questions on my help? All right, all good. And then upload the PDF and everything after the lecture. And hopefully my computer will recover now. All right, so thank you. And then hopefully, yeah, just remember, get on top of your assignment for you. All right, thank you. Bye-bye.